Well, now we're ready to do the very last homework of Chapter 2. That's 2.3b. There are 5 points, which does seem like quite a bit. That is kind of quite a bit. Problem 5, though, is extra credit, and the majority of this homework is completing our MATLAB code to take advantage of sparse structures, in particular tridiagonal systems. So last time we were able to reduce the amount of computations that we did by taking advantage of the tridiagonal structure. This time we're not only going to do that, but we are also going to try to reduce the memory that's required to store the system. Now that's going to make a bit of a challenge because we're going to put it into a single dimensioned array, whereas logically we're trying to work with a doubly dimensioned array. So that's going to be a little bit of a problem. So in the lectures, we looked at 2 matrices. Matrix A that was putting everything in a big line, single dimensioned array, and a matrix L that kept track of what the logical row and column locations were had we really put it in the dense form. Now, because we know this is tridiagonal, and we're going to have a structure on how we lay in the main diagonal and the super diagonal and the subdiagonal into our linear one-dimensional array, we can figure out where everything ought to be without this matrix L. So rather than creating the matrix, we're going to create an index function. And the index function will receive row and column locations, as well as the row dimension, which will be the same as the column dimension. And it will return a single index to tell us where in this long vector A we'd find the value that we want. So in problem 1, all we're trying to do is find out how big A has to be in terms of n. I think you know how big A has to be if it were a doubly dimensioned array, but how big would it be if all you did is store the main diagonal, the super diagonal, and the subdiagonal? So that's worth 5 points. The next thing that we're going to do is start constructing our MATLAB code. We'll go back to homework 2.3a and take a copy to form 2.3b. We'll continue to load the A3 data set, which really loads it in non-sparse form, but your first step is to convert it to a sparse form, really create a new matrix, which we'll call A, that's only one-dimensional, and to lay in all the data like we described, the subdiagonal, the main diagonal, and the super diagonal. And I think that's the order I ask you to do it in, but it really doesn't matter what order you put the diagonals in as long as you keep track of how you've constructed them. So that's part 2. Now you're going to continue to build that same code to accommodate the sparse system. Now you've already got your logic perfectly debugged using the sparsity in your numerical calculations, but still all those zeros are stored out there. So since the structure of the matrix A has changed, you're going to need to revise the code in order to accommodate this new single dimension structure. Get it to work, print out your matrix A, again this one big dimension matrix A, vector B, and X, and make sure that X is the same solution you got in 2.3a. Okay, so that's the third part. The fourth part is a little calculation on the side that asks, hey, which is more efficient using this, this new form that we've got, this sparse form, or the old one? Well, I think you can probably tell that the old one's going to be a lot less efficient from a memory point of view, but maybe for really small matrices, it's more efficient. You need to check that. Is there some row dimension for which the new sparse system becomes more efficient, but prior to that, it isn't? So I want you to look into that. How would you go about doing that? Finally, is extra credit. Go back to the text, go to page 101, problem 4 in this computer exercise 2.2, and this time go back to homework 2.1 MATLAB program because we just want to keep this simple, and create the Hilbert matrices with n equals 5, 10, and 20. Do them one at a time. And you'll need to write a MATLAB program to generate this. And once you generate it, calculate the residual variable, we'll call it R, after you solve it, and try to determine if this matrix is getting to be a real problem with respect to stability. Now, you can use the condition command that's in MATLAB and just simply apply it to each matrix and see if the condition of the matrix is getting progressively worse. It should be. You'll notice by the time you get to 20, even 20, less than 20, it's almost useless to try to solve this system, which is weird because this system actually is non-singular. So take a look at that and go back to your book and take a look at what they say about these very unstable systems. Okay, so let's take a look at some hints for problem 1 of 2.3b. So you're going to just basically predict storage requirements. So this is not a MATLAB program, this is just an algebra problem. And go to your sparse matrix and you'll need to figure out how many bytes it requires. Well, you'll need to look at the main diagonal, how many entries are there, how many are in the super diagonal, how many in the subdiagonal. Remember, this is for an arbitrary n by n matrix. So how many are you going to get? We need to keep in mind that we are using double precision reals. How many bytes are required for double precision reals? Go back and look that up if you don't remember. And every single one of the values you're storing requires that many bytes. Okay, so after you figure that out, add up all these bytes. How many do you get? And you should end up getting a formula. It will be a polynomial, a very simple polynomial, that will tell you exactly how many bytes you're going to require. Remember, there's no matrix L because we're converting that concept into a function. So we simply just won't worry about it. Okay, let's go to problem 2 and some hints. Okay, we're going to load our data from A3.xl, just like we did in the prior homework. We're going to use the usual non-sparse manner. So you'll need to convert that to a sparse form. Call the sparse form A. This sparse matrix must be one-dimensional. And that means you're going to have to load it up in a manner that you don't store structural zeros. Structural zeros are those that are not in the main, super, or sub diagonals. So you're simply going to avoid those altogether. You start with a subdiagonal, then load up the main diagonal, then load up the super diagonal in that order. So they just are butted up next to each other in this single dimensioned array. Okay, later you're going to write a function called L that, given row and column, and actually the row dimension, I should add that here as a comma n, you'll see that later, and that will return the location within this sparse matrix A for which the logical value at ij exists. So you're used to referring to everything in terms of A of ij. You're going to have to now return L of ij and pass that as a single parameter to the singly dimensioned array, unlike what we had before when we used the conventional matrix. Okay, so that should take care of step 2. Okay, when we go to step 3, you need to complete the program so it works just as well as it did in 2.3a, but using that sparse matrix form. So that means you're going to have to use this function that uses the 2-coordinate system and converts it into a single coordinate system or a single index system. Now, that could be a dangerous thing to do all in one step. If you try to write that function and just use it right away, 99% chance you're going to make a mistake and you're not going to know where that mistake is. So what I would recommend that you do is, for debugging purposes, write a new little main program that does nothing but exercise this L function that you're trying to create. And pass every combination of I and j into it and see if it gives you the locations that you were expecting it to give you in the single dimensioned array. So I'd really recommend doing that. You don't have to, but if you do it, it'll save you a lot of time. Okay, now it says copy the script 2.3a. We've already done that, so that's already done for us. But when you do bring it in, you will want to initialize a to be the right size. Well, you've already calculated the size that a is going to have to be in part 1. So set up that many zeros in advance just to simply initialize the thing. Then go back to the A3 matrix that you loaded in and run down the subdiagonal and start putting it in A, just in order. And then run down the main diagonal and keep adding it to A. And then go down the super diagonal and do the same thing. Then you know exactly what order the data is relative to the logical two-dimensional structure. Okay, now, another thing I recommend you doing, because your code is getting close to being used, is comment out the loading of A3.xl. It's too big. It's a 10 by 10 system. It's too big for suitable debugging. So just hard code into your code some simple 3 by 3 tridiagonal that's not singular, and use that first to make sure this thing works. It'll really speed up the process. You can find out where the problems are easier, get all that debugging done, and then go back after you've debugged it and bring up your A3 data, or uncomment that and take out your little 3 by 3 structure that you created. Believe me, it'll save time if you do it that way. Step 4 asks, how big a matrix do you have to have before it's really worth it to use a sparse system? So does it take a 10 by 10, or is maybe everything below a 10 by 10 is really better off if you just use a regular system? Maybe there's too much overhead with using a sparse system. Now, when we say overhead, the only thing I really care about is storage space. Now, you already know how many entries are in a conventional square matrix. Think about it. The row dimensions n and the column dimensions n, how many values are stored in the conventional matrix? Then you could ask how many entries are stored in the sparse matrix. Well, go back to problem 1. It gave it to you in bytes. You just need to now change that to entries. How many entries are in the sparse matrix system? So there's two things you could do to answer question 4. You could write a little Excel program that calculated for every value of n starting with 1, how many entries there are in a conventional matrix, how many entries there are in a sparse matrix, and see when they cross over. That would be a good way to do it. Another way to do it would be to just simply equate the two formulas you've already created for these two conditions, and set them equal to each other, and then take the biggest integer greater than the value that you get. Either way is fine. You'll get the same answers, and it's fine. Okay, there's no hints for problem 5, and so we're done now with the hints section, and and give it a shot. We'll come back in about 3 days, and we can check out to see what the solutions are.